Okay, this is lecture 19 of A2 metric spaces, and in this lecture we're going to continue to explore properties of sequentially compact metric spaces. So we introduced the notion of sequential compactness in the last lecture. Let's just briefly recall that it states that if you have a sequence in the space X, then it has a convergent subsequence. So that's what it means to be sequentially compact. First thing we're going to look at is the behavior of this notion of sequential compactness under continuous maps. And it behaves very nicely. So here's a lemma. The image of a sequentially compact metric space under a continuous map is a sequentially compact space. And a consequence of this is that if I've got two homeomorphic metric spaces X and Y, which means that there's a continuous map from X to Y and another continuous map from Y to X, and those two are inverse to one another. If one of those spaces, say X, is sequentially compact, then so is Y. In other words, sequential compactness is a homeomorphism invariant, unlike the notion of completeness that we saw earlier in the course. Let's prove this lemma. Suppose that X is a sequentially compact metric space and that I have a continuous map F from X to Y. I'm interested not in all of Y, but just in the image F of big X. And let me take a sequence of elements in there. So we'll call it sigma, and let's suppose that it consists of the points F of X sub n from n equals 1, 2, 3, and so on. Now we'll look at the sequence of xn's in the space X. Because X is sequentially compact, that sequence has a convergent subsequence. Let's call it X sub n sub k equals 1, 2, 3, and so on. And so that sequence tends to some point A. Let's say X sub n sub k tends to A as k tends to infinity. But F is a continuous map, and we know that continuous maps preserve limits. So therefore, F of X sub n sub k tends to F of A. But now I've found for myself a subsequence of the sequence sigma which converges, namely the sequence consisting of the F of X sub n sub k's for k equals 1, 2, 3, and so on. That sequence converges to F of A. So an arbitrary sequence of elements of F of X has a convergent subsequence, therefore F of X is sequentially compact. Here's a corollary of that. If I have a continuous real valued function on a sequentially compact metric space X, well then I've just shown that its image must be sequentially compact. And I showed in the last lecture that that means that, that its image is closed and bounded. So if I have a map F from X to R, and if R is sequentially compact, its image is closed and bounded, which means, in particular, that F is bounded and attains its bounds. So I think in the special case where X is closed 0, 1, this is a fact that you've seen in prelims. So a continuous function on a closed and bounded subinterval of R attains its bounds. But now we've generalized that fact, replacing closed 0, 1 with an arbitrary sequentially compact metric space. Let's turn now to another topic, and this is a nice fact. It turns out that if you have a real valued continuous function on a sequentially compact metric space, then it's automatically uniformly continuous. Let's have a look at the proof of that. Let's call the space X and the function f. And suppose that f is continuous, so f maps from X to R, it's continuous, but that it's not uniformly continuous. Well, if it's not uniformly continuous, then there must be some epsilon such that there's no delta that works for all of the points in the space simultaneously in the definition of continuity. Otherwise, it would be uniformly continuous. So there's an epsilon greater than 0, such that we cannot take delta equals 1 over n in the definition of continuity for certain points. So in other words, we can find for every n, 2 points an and bn of x, such that the distance between an and bn is less than 1 over n, but the distance between f of an and f of bn is at least epsilon. So if you think about this, it's maybe a little bit tricky to see this, but this follows if you assume that the function f is not uniformly continuous. Because if it wasn't true, then for every epsilon, there would be a choice of n such that I can take delta equals 1 over n in the definition of uniform continuity. Okay, so we have these ANs and BNs. Now, X is sequentially compact, and so the ANs have a convergent subsequence. So we'll call that subsequence A sub n sub k, k equals 1, 2, 3, and so on. And that subsequence converges to some point L. Now, corresponding to that subsequence will be a subsequence of the B's, namely the subsequence of the B's with the same indices. So that's the subsequence B sub n sub k, k equals 1, 2, 3, and so on. Now, nobody said that that sequence converges to a point. It might well not do. But actually, well, it does, because the distance between A sub n sub k and B sub n sub k tends to 0. So the distance between A sub n sub k and B sub n sub k is by definition less than 1 over n sub k, and that tends to 0 as k tends to infinity. So in fact, B sub n sub k does converge to L, the same value of L, as k tends to infinity. Okay, let's continue with the proof. So let me just flip back to the previous slide. So we've got these two sequences, A sub n sub k and B sub n sub k, and they both tend to L. Now at this point, the original sequences AN and BN are not really so important anymore. And to avoid carrying around this double subscript, which can get very tedious, I'm going to relabel. So now I'm going to suppose that I have sequences AN and BN, with the limit of AN being the same as the limit of BN being L, and the distance between f of AN and f of BN being greater than or equal to epsilon for all n. So this is just a relabeling. It might have been slightly less confusing if I'd called the new sequences, I don't know, Vn and Wn, but I didn't. So this is just a device to get rid of the double subscripts. Now, f is a continuous function at L, and if I apply the definition of continuous function with epsilon over 2, I get that there's a delta positive, such that whenever the distance from L to x is less than delta, the distance from f of L to f of x is less than epsilon over 2. That's just the definition of what it means to be continuous at L. Now, AN and BN tend to L, and therefore if n is big enough, the distance between AN and L and the distance between BN and L, they're both less than epsilon. So we have the following chain of inequalities. So first of all, just by assumption, or by construction at the top of the slide, the distance from f of AN to f of BN is at least epsilon. But on the other hand, by the triangle inequality, the distance from f of AN to f of BN is at most the distance from f of AN to f of L plus the distance from f of L to f of BN. But now, using the definition of continuity and the fact that the distance from L to AN and the distance from L to BN are less than delta, I see that these two quantities, the distance from f of AN to f of L and the distance from f of L to f of BN, well, they're both less than epsilon over 2. So when you add them up, you get less than epsilon. And that shows that epsilon is less than epsilon, which of course is absolute nonsense. So that's a contradiction. So just to recall, I assumed that I had a continuous function from x to r, where x is sequentially compact, that wasn't uniformly continuous. And then I eventually managed to get a contradiction. So we were wrong to assume that f is not uniformly continuous, and that proves the result. Now we'll turn to a different topic, which is how sequential compactness behaves under taking products of metric spaces. Now it's been some time since we've looked at the notion of a product of two metric spaces, so I shall just recall what the definition is. Remember that if you've got two different metric spaces, x with a metric dx and y with a metric dy, then their product x cross y can be turned into a metric space, and the metric d sub x cross y is defined as follows. The distance between x1, y1 and x2, y2 is the square root of the x distance between x1 and x2 squared plus the y distance between y1 and y2 squared. So that's the definition. And what I'm going to prove is that the product of two sequentially compact metric spaces is sequentially compact. So this notion behaves well under products. And a lemma will be necessary in the proof of that proposition. And this is about when sequences converge in product spaces. So I'm going to need the following lemma. Take two spaces x and y, then a sequence xn comma yn, n equals 1, 2, 3, and so on, in x cross y. Well, that converges if and only if each of the individual sequences xn and yn converge in their respective spaces. So if and only if xn converges in x and yn converges in y. We'll prove the lemma first and then use it to deduce the proposition. So let's prove the lemma. Well, we have these two projection maps that take a point x comma y and map it first to x. That's called projection map px. And the projection map py takes the point xy and maps it to y. Those are both continuous maps. That's an easy exercise. In fact, they're both Lipschitz maps with Lipschitz constant 1. So it follows that if I've got a sequence of xn, yn's that tends to a point AB, then because continuous maps preserve limits, well then the limit of the xn's is the limit of the px's of the xn, yn's, because px is continuous, which is then px of AB, which is A. So just using the continuity of these two projection maps tells you that xn tends to A and that yn tends to B. In the other direction, suppose that xn tends to A and yn tends to B. Well, then just compute the distance between xn, yn, and AB. It's bounded. Well, it's the square root of the distance from xn to A squared plus the distance from yn to B squared, and that tends to 0 as n tends to infinity. To make it less than epsilon, for instance, well, I don't know, you could just choose n sufficiently large that the distance from xn to A is less than epsilon over 2 or something like that, and the same, the distance from yn to B. So that's the proof of the lemma. So let me just repeat what it said. If I've got a sequence of elements in a product space, x cross y, they converge if and only if they converge coordinate-wise. Let's return to the proof that the product of two sequentially compact metric spaces is sequentially compact. That's the proposition that I stated a couple of slides ago. Now the notation here becomes a little bit hair-raising. We have to deal with some triple subscripts. So let's take a sequence in x cross y consisting of pairs xn, yn, n equals 1, 2, 3, and so on. So we've got the sequence of xn's, we'll call that sigma, and because x is sequentially compact, that has a convergent subsequence that I'll call sigma primed, consisting of the x sub n sub k's for k equals 1, 2, 3, and so on. So there is some subsequence x sub n sub k, such that x sub n sub k tends to A as k tends to infinity. Now consider the corresponding subsequence of y sub n sub k's, k equals 1, 2, 3, and so on, in y. Now this doesn't necessarily converge, but y is sequentially compact, so there's a further subsequence of it, and this is where we need the horrible triple subscript, y sub n sub k sub r equals 1, 2, 3, and so on, such that that subsequence converges to a number b as r tends to infinity. So it's a bit of a mouthful. Y sub n sub k sub r tends to b as r tends to infinity. Now let's look back at the x's again. Let sigma double primed be the corresponding subsequence of the x's. So that is to say the x sub n sub k sub r's, r equals 1, 2, 3, and so on. Now whatever that sequence is, it's a subsequence of sigma primed, because the n sub k sub r's are a subsequence of the n sub k's. So sigma double primed is a subsequence of sigma, but sigma converges to A. and so sigma double prime converges to A as well. So I've now got simultaneously the x coordinates converging and the y coordinates converging. So x sub n sub k sub r and y sub n sub k sub r tend to A and B respectively, and therefore by the lemma, the pair x sub n sub k sub r and y sub n sub k sub r tends to the pair AB as r tends to infinity. So I've exhibited a convergent subsequence of the original sequence of pairs xn, yn. So that's quite tricky. I had to apply sequential compactness twice, which is probably not too surprising because I need to use sequential compactness in x and I need to use sequential compactness in y. I've got to use the assumptions of the proposition. But to notate it required this rather awful triple subscript notation. So product of two sequentially compact metric spaces is sequentially compact. Okay, so just to finish, I want to record a result that's sometimes known as the Bolzano-Weierstrass theorem. I've already claimed that the fact that the closed interval 0, 1 is sequentially compact is the Bolzano-Weierstrass theorem. But the same name is sometimes given to a more general result that holds in R to the n. So sometimes we call this the Bolzano-Weierstrass theorem, that any closed and bounded subset of R to the n is sequentially compact. Let's prove that. Let's call the set X. So X is a closed and bounded subset of R to the n. Now X is bounded and therefore it's contained in some bounded closed cube minus m to the n. But the Bolzano-Weierstrass theorem on R, well, that tells you that the closed interval from minus m up to m is sequentially compact. But I've just shown that the product of sequentially compact metric spaces is compact. I mean, I showed that the product of two sequentially compact spaces is compact, but by a trivial induction, the product of n sequentially compact spaces is also sequentially compact. Therefore, the cube minus m to the n is a sequentially compact metric space. But we proved earlier that a closed subset of a sequentially compact space is sequentially compact. And X is precisely such a set. So X is a closed subset of minus m to the n. And therefore X is sequentially compact. So this is what's sometimes known as Bolzano-Weierstrass. A closed bounded subset of R to the n is sequentially compact. And then you can combine this with the result I proved at the start of the lecture to conclude, for example, that a continuous real valued function on a closed and bounded subset of R to the n is bounded and attains its bound. This is lecture 20 of A2 metric spaces, and we're still talking about sequentially compact metric spaces. The main aim of this lecture is to state and prove a big theorem about sequentially compact metric spaces, namely that they are the same as the complete and totally bounded metric spaces. Before stating that, we need to say what's meant by a totally bounded metric space, and we're going to motivate that definition a bit as well before we get to it. So let's start by proving a sort of baby theorem in this general direction. So I'll prove the following proposition. A sequentially compact metric space is complete and it's bounded. So not totally bounded, like I just said, just bounded. Let's prove that. Well, let's call the space X. Suppose X is sequentially compact. We've already shown that X is bounded. So I just want to show you that X is complete. Well, to do that, let's take a Cauchy sequence, Xn, in big X. Xn, n equals 1, 2, 3, and so on. Now we need to apply the sequential compactness at some point, so let's apply it now. We can find a convergent subsequence of this Cauchy sequence. So let's call that subsequence x sub n sub k equals 1, 2, 3, and so on. So that is convergent and we'll give its limit the name a. So the limit as k tends to infinity of x sub n sub k is a. Now I claim that when you have a Cauchy sequence, and if a subsequence of it tends to a limit, then that pulls the whole of the rest of the sequence along with it as well. So here's the key claim, that in fact the whole sequence xn converges to A. Well, let's let epsilon be greater than 0. We'll write down what it means for xn to be Cauchy, but with epsilon over 2 in the definition. So there's some capital N, such that if little n and little m are greater than or equal to capital N, then the distance between xn and xm is less than epsilon over 2. Let's also write down what it means for the limit as k tends to infinity of x sub n sub k to be A. So this means that if k is big enough, then the distance from x sub n sub k to A is less than epsilon over 2. And if I choose k big enough, then I can also make sure that n sub k is greater than or equal to capital N. So let's fix a value of k that satisfies those two requirements. N sub k is greater than or equal to capital N, and the distance from x sub n sub k to A is less than epsilon over 2. And now we'll put these two things together. So suppose that little n is greater than or equal to capital N. By the triangle inequality, the distance from xn to A is less than or equal to the distance from xn to xn sub k, plus the distance from x sub n sub k to A. And those two quantities are both less than epsilon over 2. So the fact that the distance from xn to x sub n sub k is less than epsilon over 2 follows from the Cauchy property, and the fact that both little n and n sub k are greater than or equal to capital N. And the fact that the distance from x sub n sub k to A is less than epsilon over 2 follows just from the fact that the limit of the x sub n sub k's is A, and my choice of k. So what have I shown? Epsilon was arbitrary, and I've exhibited a capital N such that if little n is greater than or equal to capital N, the distance from xn to A is less than epsilon. And of course, that's exactly what it means for the sequence xn to tend to A. So I've shown that every Cauchy sequence in X has a limit, and that, of course, means that X is complete. So a sequentially compact metric space is complete. Now, it turns out that the converse of that proposition is not true. So there do exist complete bounded metric spaces which are not sequentially compact. And I want to give you an example of that. So we'll consider the space of all bounded continuous functions on the real line, together with the subnorm and the metric associated with that. I'm actually not going to work in the whole space, I'll just work in the closed unit ball about 0, so the set of all bounded continuous functions whose subnorm is less than or equal to 1. So that's manifestly a bounded metric space. It's also complete, so we've shown that earlier in the course. But I claim that it isn't sequentially compact, and I'm going to show you a sequence of functions in this space that has no convergent subsequence. Now we'll define them all as shifts of a single fixed function phi. Now when you write down the formula for phi, it looks a bit complicated, but actually this is a very simple function. It's just a tent function, a spike, which is 0 except between -0.5 and 0.5, and it takes the value 1 at 0, and it's piecewise linear between -0.5 and 0, and between 0 and 0.5. So if you want to be formal about it, this function is defined by phi of t is 2t plus 1 between -0.5 and 0, 1 minus 2t between 0 and 0.5, and it's 0 outside of closed -0.5 plus 0.5. And then we'll define a sequence of functions fn as follows. So fn of t is phi of t minus n. So these are kind of shifted spikes. This is a spike of width 1 about the point n. So they all lie in this metric space X because they all have subnorm 1. However, if I take two different such functions, fn and fm, well, fn of n is 1 because that's phi of 0. But fm of n is 0 because n minus m will lie outside of the interval minus a half up to a half. So what this means is that the sup norm of fn minus fm, just by plugging in the value n, we see that that's equal to 1. And so this sequence definitely has no Cauchy subsequence. Even with epsilon equals 1 in the definition of Cauchy sequence, there's no Cauchy subsequence. And so hence it certainly has no convergent subsequence. So this is an example of a complete and bounded metric space which is not sequentially compact. So in other words, the converse of the proposition I stated on the last slide fails. So to get a classification that does have a converse, we need to upgrade the notion of bounded to what's called totally bounded. Let me tell you what total boundedness means. A metric space is said to be totally bounded if for every epsilon you can cover it with finitely many balls of radius epsilon. Okay? And the theorem is that a metric space is sequentially compact if and only if it's complete and totally bounded. So just to return to the definition of total boundedness, I mean, I think it sort of speaks for itself. It's an easy exercise to show, for example, that the closed interval 0, 1 is totally bounded. You can cover that by about 1 over epsilon intervals of radius epsilon. So it's definitely totally bounded. In general, we say nothing about how many balls of radius epsilon might be required, just that for each epsilon, there's some finite collection of balls of radius epsilon that covers the space. The number that you need could grow extremely rapidly as epsilon becomes smaller. So the main theorem, one of the big theorems of the course, a metric space is sequentially compact if and only if it's complete and totally bounded. So let's have a look at the proof of that theorem. There are two directions, an if and an only if. So we'll do the only if first, for the simple reason that we've already done most of that. So suppose that X is sequentially compact. I want to show that it's complete and that it's totally bounded. But we've already shown that it's complete. So all we need to do is show that it's totally bounded. Suppose it's not totally bounded. That must mean that for some epsilon, we cannot cover X by finitely many open balls of radius epsilon. But that then means that we can construct a sequence using the greedy algorithm that has no convergent subsequence. So how does that work? Well, just inductively, we're just going to choose x1, x2, x3, and so on to be separated pairwise by at least epsilon. So for every pair of distinct I and j, the distance from xi to xj is greater than or equal to epsilon. So to spell that out, suppose I've already chosen x1 up to xn. It's not possible to cover big X by finitely many balls of radius epsilon, and therefore the balls centered on those xi's, so centered on x1 up to xn, and with radii epsilon, they don't cover X, because if they did, that would be a finite cover of X by balls of radius epsilon. So they don't cover X, and therefore there has to be a point x sub n plus 1 in X, which doesn't lie in any of those balls. So that gives you the next element of the sequence. And it's clear just immediately by construction that the distance from xn plus 1 to any of the earlier points is greater than or equal to epsilon. So by a greedy algorithm like this, you can construct an infinite sequence such that the distance between any pair is greater than or equal to epsilon. And it's clear that this sequence cannot have a convergent subsequence. So we were wrong to assume that X is not totally bounded. So a sequentially compact metric space is complete and totally bounded. Now the other direction is a little bit harder. Suppose now that I've got a complete and totally bounded metric space, and I want to prove that it's sequentially compact. So we're going to apply the total boundedness assumption, not for every epsilon, but when epsilon is 1 over a power of 2. So this is a sort of what we'd call a dyadic argument. Dyadic means different powers of 2. So for each power of 2, 2 to the minus m, these are going to get smaller as m gets larger. So for each radius 2 to the minus m, there is, by assumption, a finite collection of open balls of radius 2 to the minus m, which cover X. So we don't need to be very specific about what their centers are. I'm just going to call them B1 to the m up to B sub km to the m. So km is the number of those balls. We can't say anything about what it is other than that it's just a finite quantity. So that's set up various covers of X by finite collections of open balls whose radii are powers of 2, inverse powers of 2. Well, now let's take a sequence of elements of X, call it sigma. What I want to do to show that X is sequentially compact is to find a convergent subsequence of sigma. Well, sigma is an infinite sequence, and I've only got finitely many balls of the first level, if you like, so that of radius 1, 2 to the minus 0. So let's look at those balls B1 to the naught up to B sub k naught to the naught. Well, there's finitely many of them, but infinitely many elements of the sequence sigma, and so by the pigeonhole principle, one of those balls contains infinitely many elements of the sequence sigma. Well, let's call that ball B to the naught. Might be B1 to the naught, might be B2 to the naught, but we'll just call it B to the naught. And let sigma to the naught be the infinite subsequence of sigma consisting of the elements of sigma that lie in that ball. So by construction, it is infinite. So I've now got a subsequence sigma to the naught of sigma, and all of the elements of that subsequence are contained in just one ball of radius 1. Well, now I'm going to repeat the same argument, but for the balls of radius 1/2. So there are finitely many balls of radius 1/2, B1 to the 1, up to BK1 to the 1, which cover X. And so by another application of the pigeonhole principle, one of those contains infinitely many elements of this new subsequence, sigma to the naught. So let's call that ball B to the 1, and let's let sigma to the 1 be the finite subsequence of sigma to the naught of elements contained in that ball. I should say this superscript notation here, it's just a labeling. I'm not in any sense suggesting that we should raise sigma to a power. So sigma to the brackets 1 is just a notation meaning the first element in the sequence, of first stage of the construction, if you like. So we've done a 0th stage, which led to sigma to the naught, and now we've done stage 1, which leads to sigma to the 1. So sigma to the 1 is a subsequence of sigma, and all of its elements lie in this ball B to the 1, which is a ball of radius 1/2. Now we just continue this way. The next step would look at the balls of radius 1/4, then we'd look at the balls of radius 1/8, and so on. And at each stage, we refine our subsequence to a new subsequence, sigma to the 2, then sigma to the 3, and so on. And what happens is that sigma to the r, well, all of the points of that are contained in B to the r, and sigma to the r is a subsequence of the previous subsequence, sigma to the r minus 1. So you can only begin to imagine how this might look if you use sort of double, triple, and so on subscript notation. It becomes impossible. Right, so we've done this construction. And now we come to the key idea, which is to use a diagonal argument. So out of that collection of subsequences, we'll consider the sequence sigma star obtained by what's called a diagonal argument. So the ith element of sigma star is by definition the ith element of sigma to the I. Now this sigma star is a subsequence of sigma, just by the way the construction works, because all of the sigma to the i's are subsequences. And if we write xn, n equals 1, 2, and so on, for this sequence, this subsequence sigma star, then because of the way the construction works, xn lies in the ball B to the r whenever n is greater than or equal to r. So that maybe requires a moment's thought, but that follows from the way we set the construction up. So we've got a sequence sigma star x1, x2, and so on, such that the nth element xn lies in this ball b to the r. And remember, b to the r is a ball of radius 2 to the minus r. But that makes it really clear that sigma star is a Cauchy sequence, because if you give me epsilon greater than 0, just choose a capital N such that 2 to the minus capital N is less than epsilon over 2. And obviously there will always be such a capital N. And then if little n and little m are greater than or equal to capital N, well, by construction, xn and xm, they both lie in the ball b to the n, b to the capital N, and the radius of that ball is 2 to the minus n. And therefore the distance between xn and xm, well, by the triangle inequality, it's bounded by epsilon over 2 plus epsilon over 2 equals epsilon. So what I've done, I started with a sequence sigma, and by this quite complicated argument of applying the pigeonhole principle infinitely many times and then passing to a diagonal sequence, I've extracted a Cauchy sequence from the original sigma. So I found, given an arbitrary sequence sigma to start with, I've passed to a subsequence of it that's a Cauchy sequence. And one thing to note here is that actually I've not used the completeness of X at this point at all. All I've used is the total boundedness of X. But of course, now I've got a Cauchy sequence. Now is when I'm going to use the fact that X is complete. Because a Cauchy sequence in a complete metric space, of course, converges. And so this subsequence converges. And now from my arbitrary original sequence sigma, I've extracted a convergent subsequence. And that's, of course, exactly what it means for X to be sequentially compact. So I think this is the most difficult theorem in the course, really. This fact that being sequentially compact is the same as being complete and totally bounded. So in particular, this last part where we showed that a complete and totally bounded metric space is sequentially compact is quite difficult because it involves this repeated subsequence argument followed by a diagonal argument.